Welcome, welcome, welcome. All right, today I'm going to talk to you all about prompt learning. Um, Hopefully, we have a good next 20 minutes together. So, a little bit about what I do. One of the founders of Arise AI. Arise AI is one of the leaders in AI observability. We help teams go all the way from development to production. So, we help teams actually trace their applications, evaluate them. We're going to talk a little bit about Swix's controversial statements today about the evals really matter, and then also actually help them develop and iterate using prompt iteration. So let's jump into it. So this is actually a real post from Hacker News that I just put on the slide, which is, I think, just really emblematic of what people are feeling today. Somebody's asking, are there any real examples of AI agents doing work? And he's asking kind of, anyone have an example which I understand to be intelligent that isn't just a glorified or rebranded workflow automation? And I think you get a sense of this kind of skepticism from people who are building with agents today because they're just really brittle. It's really hard to get them to work in the real world. And I think what we're starting to see is that there's common patterns that really good agents are starting to have. And when they don't have them, they tend to be brittle. One of them is the system instructions, if they remain static and they're not consistently kind of being updated. This is what we're going to dive into today. That tends to keep it so that the agent doesn't actually learn from its environment. You have, I think there's screenshots now of all the to-do lists inside of Cursor and inside of Claude, but actually planning and being able to have, planning that updates is something that's starting to become a really common pattern in agents. How they call tools or the guidance around tools tends to be something that I think some of the better agents that we're using do really well. And then context engineering is a whole domain that, when the context isn't passed correctly, either between agents in a handoff, we start to realize that this is where agents end up tending to be brittle. But today, what we're going to actually talk about is system prompts. This is a really viral tweet that Andrea Karpathy kind of tweeted in May. And I think he's actually starting to hit on something which is really interesting in this space. What he's talking about here is that there's a major paradigm kind of missing for LLM learning. He's given it a name, system prompt learning. He's like pre-trainings for knowledge, fine-tunings for habitual behavior. But there's a lot of human learning that actually feels like a change in the system prompt. So you learn something from your environment, something doesn't go right. You end up taking a note for yourself. Hey, next time I see this scenario, I'm going to act like this. And this needs to go somewhere. And if you end up putting it in pre-training, I mean, that's a lot of work. It's a significant amount of effort. You can do it in fine tuning. Again, significant amount of work. But you actually have English feedback and an explanation that you can just put in to the system prompt. And this is significantly kind of higher dimensional feedback than just a scalar score with typical, if many of you guys are familiar with like RL type of approaches. And so why not use these system prompts to actually pass in this type of feedback and make sure that the system prompts don't just remain static? This is actually Claude's system prompt that got leaked on GitHub a couple of months ago. 24,000 characters, 18K words. And you can see here that it's pretty detailed in terms of all sorts of conditions and how Claude should behave. And I think the key takeaway from this is that this didn't happen in a single iteration. No one just wrote the system prompt overnight and then put it into production. This was meticulously shaped over collecting data, looking at where Claude didn't do well, and then actually using that to iterate on the system prompt. If there's anything you take away from everything I've said so far, it's that the system prompts are actually really key to building effective agents. And as agent builders here, that is something that you can actively shape. And there's all sorts of different prompt optimization approaches that we're going to talk through today that you have in your toolkit. There's kind of the old approach, which is more traditional RL type approaches. So the traditional RL type approach, what you have is a scalar reward. You have a scalar reward, there's some sort of gradient descent type algorithm that actually uses it to go update the RL system, requires a lot of examples. It's really expensive in this world. There's other type of approach called MetaPrompting, where basically you are now actually updating the prompt itself, but you're still using kind of a scalar score to identify what are the tweaks in the prompt, the system prompt you should actually make. What we're going to be talking about today is kind of a new approach, prompt learning, inspired by Karpathy, which actually uses the English feedback, so not just the scalar scores, but it actually uses the English feedback to improve the prompt. And I'm going to show you on actually an agent, a type of agent that's really successful coding agents. So just to recap on what system prompt learning is, it basically takes the data, so this is the inputs, the outputs, also the explanations or the annotations. It takes the original prompt, you're going to pass that into a MetaPrompt, and then you're going to get a new prompt. This is kind of the theory. Let's see how this actually works. We put this to test, and I'm going to run you through the benchmarks that we did on the Klein system prompt. So for those of you who don't know what Klein is, Klein's one of the leading open source agents, coding agents. So the entire kind of, it's entirely open source. You can go look at the system prompt today. We heavily cut the system prompt. It's like 30 pages long. But the system prompt basically has, whatever the system prompt is, and then a section where you can actually add rules. So if you're familiar with like cursor rules, Klein also has something like, its own rules that you can go in and add. Typically, when you use the out-of-the-box Klein, the rules are empty. So we started off with kind of this was the system prompt with empty rules. And the first thing we did was run an initial benchmark. How does the initial kind of system prompt do just on its own without any modifications? We tested it on SweBench Lite. SweBench Lite is like 300 plus software engineering problems. And we ran kind of Klein on plan mode on SweBench Lite. So Klein, just for context, has both plan mode and act mode. Plan mode is basically where it generates a plan, but it's not actually generating the actual code and then running the code on the actual problem. We're actually currently working on act mode results, so hopefully I'll tweet about this soon. But we tested this using plan mode. And in plan mode, I mean, the results were, okay, as you can see, it's not great, but like around 31%, basically on SweBench Lite. And if you go in and you actually look at what, where Klein actually fails, these are some type of examples just to kind of build some intuition. So this is actually one of the problems from a library called Marshmallow. It converts complex data types. And Klein was asked to fix some type of bug where the program, if the input was none, then the program used to just crash. So can you handle that better? So Klein basically, just did exactly that. If data is none, just return. But it fixed just that single case. But the input type can actually be not just a single kind of word. It can actually be a list. It can be a complex data type. So it actually has to go in and check all these different scenarios before it can just return. So this was one type of scenario where Klein jumped to a very minimal fix without looking at what are all the different types of cases that input can be. Here's another one that kind of initially it failed at. Another kind of repository, SymPy, Python library for kind of symbolic mathematics, where basically if there was some sort of operand like 2 times a matrix, but you had some other type of operand like an @ sign, it would incorrectly behave like multiplication instead of just failing. What it should do is just like raise some type of error or suggest some type of fix. In this scenario, what it basically did was that it actually, it ignored kind of the actual Python language kind of contract around what you should do if it's, the fallback option for Python, and it wrote some sort of ad hoc fix which didn't take care of multiple scenarios. Again, another type of situation where the fix kind of looked right, but you dug in deeper and it wasn't actually the right solution. So we decided to go and actually test out prompt learning on this. We took kind of Klein, original Klein on the original kind of system prompt that it came with. We ran it across the entire kind of SweBench Lite on all the sets of problems, and it generated a whole suite of actually outputs. We then took those outputs, and then the test set we tested on SweBench actually had a golden data set. So it had the ground truth basically with the actual kind of PR, with the actual test patch, and we passed the solution that Klein generated against the golden data set or the ground truth, and we asked an LLM as a judge to actually evaluate, is this the right solution? Did it generate a plan that would actually solve this problem? We wrote a whole template. We passed those inputs in. And this is a key part that's important here. We not only just asked like correct, false, we actually asked to give an explanation. So why was it wrong? Give me a reason why. And this is important because whether you do this using an LLM as a judge or whether you do this using a human annotation, this is the English feedback that Karpathy was actually talking about in his tweet. This is the higher dimensional feedback that an LLM can actually take and use to update its system prompt rules. So we took these explanations and we passed all of this into the MetaPrompt. So the MetaPrompt now has the original prompt that we started out with, which remember had no rules. We then passed in this data. This data is what was the problem to solve, what was the solution that client came up with, and then here's the, whether it got it right or wrong, along with the explanation. All of this got passed into the MetaPrompt, and there's a lot here to unpack around how do you manage the context window, like will all of this fit, how many examples, hold that thought for a bit. But basically, all of this goes inside the MetaPrompt, and we were able to generate kind of a new system prompt. So this is just like a diff view telling you in the old world, the rules were empty. In the new world, there's all of these rules. And I couldn't fit it all on a slide, but even in something like 5, 10 loops that we did, there was close to 100 different rules. All of these different types of use cases and errors that Klein would make, and all of these got passed into the rule section. So fun fact, if you're using Cursor, if you're using Klein, this is actually something you can do today. So all of these goes into the rule. You might be asking, okay, well, does this really work? Like, what was the performance? Tell me what the benchmarks were. Okay, before I get into that, I'll just tease a little bit with the same problems that we saw earlier. So this is one where it was performing on that Marshmallow library, the SymPy library. Both of these, we actually reran this with the new updated system prompt. This time it was actually able to generate a correct solution. It's actually each one of them had a corresponding rule that was in the rules that was added to the system prompt. And overall, I think with about 5 to 10 loops, we actually saw about 15% accuracy in kind of the test performance. So something around like 30% to like 45% accuracy after 10 loops. We did a typical, just in case any of you are curious, we benchlight. We broke it up 50% train, 50% test, and we ran this across 300 kind of software engineering problems. And this took probably about 5 to 10 loops to see some sort of improvement. We also tested this on BBH, which is known for being much more difficult tasks for language models. And BBH actually has different categories of software engineering problems. And I think what we were really excited about, and we're going to share some of these results more publicly soon, but some of the more harder types of problems like salient translation error detection or snarks, we actually saw, even after just 5 loops, something that the LLM was, Klein was not doing so well on, able to see pretty massive jump in terms of performance, and actually very minimal kind of regressions in some of the other categories. So this is one where just adding the annotations and adding where actually it didn't go well was something that was able to see some pretty incredible improvements. So what's the takeaways for this group, for agent builders? We just ran this on some of the hardest, you would say most successful types of agents out there, which are coding agents. I think the key takeaway that we wanted to share with you guys is, one, collecting those errors and actually either running evals or doing any kind of annotations on them is actually really important, because you won't really be able to understand what to go fix if you're not collecting those examples. This is an example of basically one of the things that we do, which is where you trace the entire application. This is typically when you hear people talk about things like online evaluation versus offline evaluation. I mean, I think one of the things that Swix was saying yesterday in his keynote was like evals, should they really be blockers before you ship something into production? I actually really don't think they should be. I think you should ship things, you should put them into production. But I think what most people actually don't talk about is that online evals, actually running evals in production on top of your data, is probably way more important, because now you actually have the data, the traces, your logs that you can then use to identify what's working, what's not working. And that's more important because it's your own data. You're not writing some BS tests that you're using as a blocker before you roll it out. You're actually evaluating your traces, and then you trust those traces to then go back and feed it into iteration. you use, just like we did where we grabbed those annotations, we fed them back into prompt iteration. Well, while we were iterating, we were running those same evals. This is just an experimentation view where we tested those system prompt changes, we tested what rules were better, and we actually used that as almost like unit testing before we deployed it into production. And so when people tell you, oh, run evals offline, run it before you deploy, I think the way we think about it is that those are unit tests. And unit tests are important, but you can think about them as I always think real data, real production systems, getting visibility into that is often more important. Some of you guys might ask, okay, well, did prompt learning only work on coding agents? Do you really see it useful in other domains? Prompt learning is actually, we've been using it across a lot of different domains. We use it with a ton of our customers and use cases, even our own agent actually. This is another set of results that we've published around structured JSON web page generation, so more structured outputs. Basically, after 5 loops, we were able to see significant increases in kind of accuracy again here. This is interesting. We're basically here, the more the rule set kind of grew, you can see here that didn't necessarily always mean that accuracy was going to be consistently up. So actually having a differentiation in basically how much rules you actually pass in is something that you need to kind of iterate and tweak on in your use case. This is another use case, support query classification. So think more of like those customer support bot type agents. Here you can see here it goes vertical. So 1 loop all the way down to 5 loops. We were able to see about 8 to 9% kind of accuracy increase as we increase these. Big takeaway, I think what we're going to see a lot more this year people talk about is how are you consistently having the prompts learn from the environment. Some of these updates will be how I showed you, human in the loop, human kind of going and updating those system prompts. But I actually think a lot of those updates are going to be totally automated. You're going to collect data, you're going to run evals, you're going to run a prompt optimization approach, you're going to update your system prompt. And this is actually going to be a big paradigm shift in how people build agents. Awesome. Well, thank you so much for your time. I have any questions.